So if we were to naively make use of the Loewenberg-Marquardt algorithm, we will find ourselves quickly running into a cubic complexity at every iteration, since we are going to solve for the normal equation given by J transpose J delta equals to minus J transpose epsilon over here. And this, we have seen that this is equivalent to inhomogeneous linear equation of Ax equals to 0. And we all know that when we solve for this inhomogeneous linear equation for x, which is equivalent to delta over here, we have to invert this guy over here, the A matrix, in order to get solve for A, which is equals to inverse of A multiplied by B. And this incurs a cubic complexity where n over here can be very large. And this where this is actually in the order of the total number of camera parameters over all camera. So it would be 12 multiplied by the total number of camera in our 3D reconstruction, as well as the total number of 3D points. That would be 3 coordinates of x, y, z multiplied by the total number of 3D points in the scene. In the 3D reconstruction problem, this can easily be up to an order of millions of 3D points. So fortunately, we will exploit the sparse block structure in this A matrix, which is equivalent to the J transpose J matrix over here, in order to mitigate the computational complexity. More specifically, we first divide or partition the set of parameters P, which is a m-dimensional parameters, into two sets of parameter vectors, which we call A and B. So what this means is that I'm going to rewrite P into P1, P2, all the way to Pm here. And I'm going to partition this set of parameters into two sets, where I call the first set of parameters over here a vector of A, and the second set would be a vector of B over here. And I'm going to rewrite this P as A transpose, B transpose, and altogether transpose. So this, in the context of our bundle adjustment problem, A could represent all our camera parameters, and B here could represent all the parameters from the 3D points. So we can partition them into two sets of parameters that we wish to optimize over. And now the Jacobian J, which is defined as del x over del p, where x hat here represents the nonlinear function that we want to optimize over. That would be our reprojection function. In the context of bundle adjustment, you would now form a block structure of the form of A and B, where A and B here are respectively given by the partial differentiation of x, the nonlinear function, with respect to the first partitioned parameter A and the second partition parameter B, respectively. Now, after we computed the Jacobian in the partition way, we can put it together into the normal equation to compute J transpose J, which is this guy over here. And we will see that it has a very nice structure over here. And delta would also have a partition structure where the first set of this vector would be representing A, and the second set would be representing the delta increment of B. And similarly, for the right side of this normal equation, which is given by minus J transpose of epsilon, we can see that the structure would also be, the first part here is only dependent on the parameters of A, and the second part will only be dependent on the parameter of B. And we can rewrite this block over here, the J transpose J block over here, into this form, where we saw that the off diagonal here, it consists of the same parameters, but just a transpose of it. So we'll rewrite this part as W and the lower left part as W transpose over here. And then we'll write this block over here as U star, and this block over here in the diagonal block as V star in this particular form over here. Now, we further observe that if we were to multiply the normal equation with or the left and right side of the normal equation with this particular matrix over here, we'll be able to get this equation over here where we can see that in the first row, the top right uh, entry, the top right block over here would become 0 because we have this element over here, which will act as a subtraction over here to eliminate W in this particular block over here. So once we have arrived at this particular equation where the top right block over here it's equals to 0, we can make use of this to solve for delta A, because we can see that after multiplying this row over here into this column over here, delta B is being eliminated. So we will get the equation of this block multiplied by delta A equals to this particular block over here. And the only unknowns in this case would be dependent on the parameters of A. So in this particular form over here. And this is also known as the Schur's complement, and which we can use to solve for a partial block of the uh, parameters that we are interested in optimizing over. And we can also see that this form of equation, it becomes a inhomogeneous linear equation where it's equivalent to ax equals to b. This whole block here is b, and this block here is a, and delta a here becomes x, where if we were to compare this with the original normal equation over here, now we have a smaller block of x over here to solve for as compared to this, where because this x over here, it is the original parameter which consists of the parameters of a and b. That means that it's actually delta a and delta b altogether. And what this means is that j transpose j in the original form is much larger than the form that we are, the inhomogeneous linear equation that we are trying to solve for here. And we will also see that another advantage of this is that this particular block here, it's much sparser, and this can be solved efficiently using several linear algebra factorization technique. So once we have found delta A, we can subsequently solve for delta B using back substitution by the following equation that is shown here. This equation is in fact obtained from the second row of this particular equation over here, where we multiply this guy to delta A and this guy to delta B, and that would be equals to epsilon B. Since we already know delta A, we will have one equation that is consists of the unknown of delta B, and this particular equation over here would again be equivalent to ax equals to the inhomogeneous linear equation, which we can solve efficiently for x. Now, once we have computed the delta A and delta B, the update vectors of delta A and delta V, we can put it back into this equation over here to get the updated equation of P. So this is simply equivalent to Pi plus 1 is equals to Pi plus delta, where delta is the value that we have solved for in the normal equation. So since here we split this delta into two parts of delta A and delta B, we can put it back into the equation by adding it back into the respective part of A and B to get the new vector of P. And we'll do this iteratively until convergence. So we'll also follow the way that we increase or decrease lambda in the naive Loewenberg-Marquardt algorithm that we have seen earlier on. And here's a table that summarizes the sparse Loewenberg-Marquardt algorithm that I have talked about earlier on. Now we'll look at the application of the sparse Loewenberg-Marquardt algorithm on the multiple image bundle adjustment. In particular, we'll take advantage of the lack of the interaction between the parameters of the different cameras to obtain the sparse structure in our normal equation. So we'll define the measurement data as capital X over here, where each one of these x1 to xi, it represents a set of the observation on the images. So we can think of it this way, that each one of these x is actually a 3D point in the scene, which we call capital Xi over here. And it actually also contains a set of corresponding 2D points on the image. For example, xi1, that means that I'm observing this xi, this 3D point in image number 1. So I'm going to call this xi1. This means that there is a correspondence from the first image, and there's also a correspondence in the second image, which I'm going to denote as xi2 over here. So note that this 1, 2, and these indexes, it need not be consecutive, it need not be continuous here, because what this means is that we are allowing for missing data. That means that it's not possible to observe the same point over all the image frames. So it could be image number 1, image number 2, and then it jumps to image number 5, for example. So we are going to have I1, I2, and then xi5 transpose over here, and all the way to xim. This means that this particular 3D point xi is being seen in m number of images, and we're denoting small x ij as the image 2D point that corresponds to the 3D reconstructed points. And as mentioned earlier on, we're going to denote the camera parameters as A, which is denoted by A1, A2, all the way to AM, where they are all together M images in our bundle adjustment context. And each one of these parameter, AI, it represents the jth camera in the scene. And this could be a 12 by 1 vector, which represents all the parameters in our projection matrix. So suppose that we are given a reprojected point which we call xij hat here. We know that this xij is a result of the reprojection of a 3D point xi in the 3D scene. And we know that this particular 3D point would only be seen in the jth camera. That means that if I have a camera AK, for example, we will only see this particular 3D point as xij if k is equals to j. What this means is that the partial differentiation of xij hat over xaj will not be equals to 0. And in general, if k is not equals to j, what this means is that this particular 3D point would not be reprojected onto this particular image if this is ik over here. And in similar way, we can see that the partial differentiation of the reprojection will not be equals to 0 if we partially differentiate with respect to the 3D point that is reprojected onto that particular image. Suppose that I have an image which I see the reprojection of x hat I and j. I know that a 3D point whose parameter is b of k over here, it would be reprojected onto this particular image if k is equals to I over here. And what this means is that if I take a partial differentiation of x hat ij with respect to the partial differentiation of b of I, then this in general will not be equals to 0. But if I have a case where k is not equals to I, this means that this particular point will not be reprojected onto this particular image, or where I see a reprojection of x hat ij over here. And in this particular case, x hat ij over here will be independent of bk. And this means that the partial differentiation will be equals to 0. And the form of the Jacobian after we do this partial differentiation would be shown in this particular figure over here. We can see that projection matrices, which we denote as the vector of A, and the 3D points, which we denote as the vector of B over here, it's only affecting the reprojected points when we can see that it's in that particular respective camera, or it's in that particular respective 3D point. For example, in this case here, x1 and j, this 3D point is seen in the first camera. So let's say this is my a1, which is denoted by the parameters of p1 over here, and I'm going to see in this example over here 4 points inside here. So this 4 point is going to be x11, x12, x13, and x14. And we can see that these 4 points, it's only affected by the variable a1 or p1 that is denoted in this particular diagram over here. And since p1 is the parameter of the first image, we can see that in the second image, if we were to see also 4 points in this particular case over here, 4 points that is projected onto this particular image over here, which we denote as A2 over here, or P2 in this case, we can see that the P1 over here is not going to reprojected point in the second image. Hence, all the entries over here, the partial differentiation of del x2j over del P1 is going to be 0 in this block over here. But it's not going to be 0 in the first block over here, because we can see that the first camera matrix is affecting the points that is reprojected onto the first image. And similarly, the first camera matrix is not going to affect all the reprojected points. In this particular example here, there are 4 reprojected points onto the third image, which we denote as A3. So there are 4 of these points. We can see that the first camera matrix is not going to affect this, and hence all the partial differentiation of this block over here is going to be equals to 0 as well. And we can also see this in the 3D points, which we denote as the vector b here. So in this particular case, in the first image over here, we have 4 reprojections, which we denote as x11, x12, x13, and x14 over here, as mentioned earlier on. And we can see that capital X1, which is the first 3D point. So this means that I have a 3D point here, which I call x1. It's only going to be affecting one of the entries, one of the reprojected point, which is x11 over here. What this means is that x11 is the reprojection of x1, the first 3D point, into the camera image of the first camera. So we can see that it's affecting this only. Hence, taking a partial differentiation of the reprojection over here with respect to x1 is going to be a certain value over here, a non-zero value over here. But at the same time, if we look at all the other entries over here, the other 3 entries over here, which represents the 3 reprojected point in the first image, it's not going to be affected by x1, because these are caused by some other 3D points in the scene. Hence, the partial differentiation of this is going to be equals to 0 over here. And we can see that in the first image over here, the second point, which is x2 over here, which is caused by a reprojection of x2, the second point over here, it's going to be non-zero value when we partially differentiate x12 with respect to x2, and it's going to be 0 everywhere else. And we can see this trend happening in all the other entries in this block as well. So once we have computed this, we would have obtained the Jacobian matrix in this particular form. And we can see that this is indeed a very sparse matrix, where most of the entries here are equals to 0. And it's only sparsely filled in the white parts as illustrated in this particular figure. So once we obtain the Jacobian matrix, we can continue to get the normal equation, where we can compute the Hessian of J transpose J, which is in this particular format over here, as what we have described earlier on. We can also see that this is a sparse matrix in the diagonal block over here, where all these entries over here are going to be equals to 0. And now delta over here would be divided into 2 parts. The first part here would be dependent on A, which is our camera matrix, and the second part over here would be dependent on the 3D point entries, which corresponds to the partition of the blocks over here in the Jacobian matrix. And similarly, epsilon A and epsilon B, denoted by this term over here, would be divided into two parts. The first part is again dependent on the camera matrices, and the second part would be dependent on the 3D point. So we can see more clearly in this illustration over here that the first block over here, taking the second camera where I equals to 2, taking this block over here, we can see that partially differentiation of the this point x2j for the 4 points that is being reprojected onto the second image where I equals to 2. So in this case here, I'm looking at P2. So I'm looking at 4 points over here where each point represents x21, x22, x23, and x24. And in the case where I'm partially differentiating with respect to the first camera uh, matrix, this would be 0. And it would be the same for the case where if I'm partially differentiate this with respect to the third camera matrix over here, it will also be equals to 0. And the only case is that it won't be equals to 0 is when I partially differentiate this reprojection with respect to the camera matrix P2 or A2 that I denote over here. This is because this is the camera projection matrix that affects this particular image, and in turn it will affect the reprojection onto this particular image over here. And here's an illustration on how the 3D points affect the Jacobian. We can see that this is the reprojection onto the second image, the 4 points onto the second image. And we can see that it's non-zero when we partially differentiate this, the respective reprojection with respect to the 3D points that causes this particular reprojection over here. What's interesting here is that if we look at the Jacobian matrix, where we obtain the Hessian matrix as J transpose J over here, and it's interestingly that J transpose J, or the Hessian matrix, it actually represents the adjacency matrix of the graph that relates the relation between all the parameters. So in this particular case over here, we can see that there is a connection between A to 2 and 1. So here in this example over here, these are the 3D points and these are the cameras. So what this means is that this particular 3D point A is seen by camera 1 and 2 and is not seen by camera 3 and 4. And the second point B over here is seen by camera 1, 2, and 4. So what it means is that if I have an image here, which I call A and B, and I have a point where I call 1 or x1, and then another point which I call x2. So in this graph over here, it simply means that x1 is seen by both images and x2 is also seen by both images. But x3, for example, is not seen by neither of these images, but x3 over here is actually seen by C and D. That is the third and fourth camera. So x3 over here will be seen by these two camera, and x1 over here is actually also seen by C concurrently with A. So this means that this is going to reproject into C as well. And we can see that this graph over here, that relates the camera parameters as well as the 3D point, it's well represented as an adjacency matrix in the Hessian matrix over here that we compute in the normal equation. And as mentioned earlier on, once we have computed this, the Hessian matrix and the Jacobian matrix that we have seen earlier on, it's equivalent to this structure over here, which is represented by this diagram over here. So we can see that the W and W transpose is just a transpose of each other, and the diagonal over here it's actually a sparse matrix, and we can rewrite this into this form over here that we have seen earlier on when we look at the sparse Loewe-Marquardt algorithm. And we also mentioned earlier on that we can compute the Schur complement by multiplying this block of matrix over here on both sides of the normal equation, where we can see that the first half or the first block over here, it represents the camera parameters, and the second block over here represents the 3D structure. So by multiplying this, we obtain the Schur complement equation of the first row, because there's a zero here. So it effectively decouples out delta B from A. We will have an equation that with only delta A that is remaining. And we also know that this will can efficiently speed up or effectively speed up the computational power, because the number of cameras is far lesser than the number of 3D points in the normal 3D reconstruction problem. And here's what I have mentioned earlier on. We get the Schur complement equation, which is equivalent to AX equals to B, an inhomogeneous linear equation that we can solve for delta A in this particular case over here. And it's easy to invert this guy over here, because when we compute this from this block over here, it will become a block diagonal uh, matrix, and it's both sparse and symmetric, positive definite. This means that the inverse of this guy exists, and once we have computed for delta A, we can back substitute it into this equation over here multiplied by this, and when delta A now is a known vector, and which we can solve for delta B. And uh, to solve for the non-homogeneous linear equation, system of non-homogeneous linear equation, which is equivalent to AX equals to B, we can make use of many linear algebra techniques, such as the LU decomposition, where we factorize this into this A matrix over here into a lower and upper triangular matrix. So once we have a lower or upper triangular matrix, for example, we can easily solve for X over here by doing this. So LU, which represents A, multiplied by X, and B over here. So we can collectively call this U as a Y and solve this equation as Ly equals to B, where this is a lower triangular matrix. So if this is a lower triangular matrix, that means that the upper triangular part of this matrix is equals to 0, multiplied by a vector of Y and equals to B. What we can do here is that we can simply solve for this element multiplied by the first entry of Y, and then solve for this first entry, and gradually do a back substitution to solve for all the other entries in Y. So once we have obtained Y over here, we can see that Y is actually equals to U and X. We'll solve for another homogeneous linear equation where this becomes an upper triangular matrix. So what we will have here would be upper triangular matrix over here multiplied by X. We can where Y is now a known value, we can do a back substitution, solve for the first value over here that corresponds to the last element of X, and do a back substitution to solve for all the elements over here. Similarly, we can also apply the QR decomposition and the Kolesky decomposition, where QR decomposition here simply means that the Q matrix is an octagonal matrix, and the inverse of an octagonal matrix is simply the transpose. So we can solve for this as QR multiplied by X equals to B, and then we can do a Rx equals to Q transpose of B, which can be easily computed by taking the transpose. We do not need a inverse of this, which is easier to compute in this case. So once we have computed this, then we'll end up with another the system of linear equation, which we call this collectively as a Y. We will end up having to solve Rx equals to Y, where R here is a lower or upper triangular matrix that we can take advantage of the same method to solve for the unknowns of X over here. And similarly for Kolesky decomposition, which is probably the most commonly used decomposition or factorization technique to solve for the normal equation in Loewenberg-Marquardt algorithm, where we simply factorize A into a square root matrix, L multiplied by L transpose, where L here is a lower triangular matrix that we can then solve for the x in the similar way as what we have seen in the LU factorization. For more information about this, because you should have learned this in your undergraduate linear algebra course, I won't go through in very much detail except for what I have just talked about just now. And for more detail of this, I advise you to look into this textbook by Gilbert Strong, Linear Introduction to Linear Algebra. There's also very nice video lectures online that is taught by Gilbert Strong himself. And I strongly encourage every one of you to look into this if you forgot some of the basic background knowledge of linear algebra. And there are also other techniques to solve for this non-homogeneous linear equation in an iterative method, such as conjugate gradient and Gauss-Schneider algorithm. And I also strongly encourage you guys to look into this. Part of this can also be found in this particular textbook. Now, unfortunately, the normal equation cannot be solved in a naive way of just taking the LU decomposition, Kolesky decomposition, or other form of decomposition, because we will more than often face what we call the problem of fill in the this kind of factorization techniques. So what it means here is that if I were to have a matrix A in the homogeneous linear equation of AX equals to B, uh, I would one technique that I have mentioned earlier on here would be to solve this using the Kolesky factorization technique by decomposing this or factorizing A into L multiplied by L transpose. But more than often, if given a sparse matrix of A, by simply naively doing a Kolesky decomposition on the sparse matrix A, we will end up with a lower triangular matrix that is much more denser than the original sparse matrix itself. And this would not be good because we will end up taking more time in solving for the equation in the back substitution steps. And one way to resolve this is to reorder the sparse matrix of A by a permutation matrix. So permutation matrix simply means matrix that is with entries of one or zeros in the matrix, and every column and every row of this particular matrix has to sum up to one. So this means that I have to have only one ones in a particular row as well as a particular column over here. And what this means is that I'm going to reorder a permutation matrix given a square matrix over here. All the entries in this particular matrix would be reordered. That means that I will have to swap some of the entries by simply applying the permutation matrix on the A matrix. I'll not go into the detail of this. I'll just simply give you a flavor of the how to do the reordering or what does the reordering means over here. So unfortunately, this particular problem to reorder the sparse matrix is an NP complete problem, and this means that it could become intractable to compute for the uh, best permutation such that we reorder the A matrix to minimize the amount of fill-in after, for example, Kolesky decomposition. There are some approximation algorithm such as the minimum degree, the column approximate minimum degree permutation, reverse McCarthy-McKee algorithm, and the nested dissection algorithm. I will not go into the detail of this algorithm. If you are interested, you should read the related text. And here we'll see the effect of applying this fill in the permutation algorithm or the reordering algorithm to prevent fill in. Given a sparse matrix where we have 18,441 non-zero entries, for example, after applying the reordering, we'll see that we reorder these elements to become something like this, for example, by applying P transpose and P on A. So we'll still get the same number of non-zero because we are simply just reordering the entries in the sparse matrix of A. Then after Kolesky decomposition, we apply Kolesky decomposition on this matrix over here after reordering. We can see that the total number of non-zero, it becomes 78,120, which is lesser than what we began with, and it's also lesser than this example over here where we simply naively apply a Kolesky decomposition on the sparse matrix of A, and will lead to a 8.28% increase of the non-zero elements as compared to this particular guy over here. So similarly, if we were to apply a minimum degree reordering on the sparse matrix, this is what we will get. We will still get the same number of non-zero elements because we are simply reordering the entries in the sparse matrix of A. And after applying Kolesky decomposition, we can see that we end up to have 52,988 non-zero elements over here. This is still much lower than what we have over here, which is about 606,000 non-zero entries. We can see that we have the same effect by applying column count as well as nested dissection, where we will end up with a much lower number of non-zero elements after applying the Kolesky decomposition. So here's a comparison of the non-zeros after factorization. You can see that the original factorization, the naive Kolesky decomposition on the original sparse matrix, it will lead to many non-zeros over here. And it seems like nested dissection has the best performance in this particular example, where it gives the least number of non-zero after Kolesky factorization. And what this means is that because Kolesky decomposition, it turns A into LL transpose, which I have mentioned earlier on that we are going to solve this equation by grouping this together as y and then solve it as Ly equals to b. So L over here is our lower triangular matrix over here. So what this means is that if I have very few non-zero entries over here, then the number of operations that I need to do by back substitution would be far lower than the number of computation that I need in the naive Kolesky decomposition of the original sparse matrix. And this would lead to a much more efficient computation of the normal equation, which has to be done at every iteration in our Luvenberg-Marquardt algorithm. And finally, here's some open source software that is capable of implementing Luvenberg-Marquardt algorithm for bundle adjustment. So you don't have to code everything from scratch. These three libraries which helps you to do this bundle adjustment, and particularly for the problem of structure from motion. And Google Series is most commonly used in the computer vision community for structure from motion, and G2O and GT-SAM, it's more commonly used by the robotics community for visual SLAM, visual simultaneous localization and mapping. As a summary, we have looked at in today's lecture how to describe the pipeline of large-scale 3D reconstruction. In particular, we look at data association and the structure from motion. We'll leave Dan stereo to the next week lecture, and then we have looked at how to do data association using robust two-view geometry as well as the back-of-words algorithm. And we look at how to do the initialization of 3D reconstruction with two-view geometry, PMP, as well as the linear triangulation algorithm. In fact, these three algorithms are what we have learned in the past lectures. And finally, we look at the definition of bundle adjustment and how to do bundle adjustment using the iterative methods such as Newton, Gauss-Newton, and the Luvenberg-Marquardt algorithm. And that's all for today's lecture. Thank you.